Hello. For today's lab, we were supposed to use a video containing the motion of a mass swinging in an arc while oscillating on a spring to create a model that would predict the motion. The model was based around Newton's second law and the energy principle. My model matched very well with the y position of the observed motion, as is shown in this graph, where the blue is the model and the red is the observed motion. And the x position of my model matched fairly well with the x position of the motion, although as you can see there is more of a variance with the x position than with the y position for my model. The fundamental physics principles that were utilized in this lab were Newton's second law and the energy principle. Newton's second law was used to predict the motion of the mass, where the velocity and the new position was able to be calculated during each time step of the motion. The model was also able to demonstrate the energy principle, where the sum of the initial kinetic and potential energies equaled the sum of the final kinetic and potential energies in a system containing Earth, the spring, and the mass itself. Here's how I used Newton's second law to predict the motion. The forces that we considered for this experiment were the force of gravity and the spring force. The force of gravity is simply calculated by multiplying the mass times the Earth's gravitational constant, and the force of spring is calculated using Hooke's law, where it's equal to the spring constant times the length of the spring minus its relaxed length. We were not given the spring constant or the relaxed length for the spring, but we were able to derive them using these formulas. In this case, this is 4 pi squared times the mass of the object divided by the period of oscillation. T is equal to the period of oscillation for the object, and we were able to derive k that way. And using this formula, once we found k, we were able to find the relaxed length, which was 0.123 meters. Now let's take a look at the Python code. Most of the things here are simple initializations, as I've initialized the mass here. I've initialized all the values that we just calculated, ks, l naught. But here's where I've had some important lines of code. I've calculated the kinetic energy of the ball by using the formula 1/2 mass times velocity squared. I've calculated the gravitational potential energy using the mass times the gravitational constant for Earth times the ball's position. The spring potential energy, which is 1/2 the spring constant of the spring times s squared. And now in the loop, I've calculated the force of gravity, the force of the spring, the net force, and then from that I've updated the ball's position and the ball's velocity. And this is how the code looks when it's run. Okay, in the code I included the red ball, which is the observed motion, and the blue ball is the model motion. As you can see, they match each other very well. The green arrow is the net force, the blue arrow is the force of the spring, the black arrow is the force of gravity. But you see the balls match each other very well all the way through the motion. So I can say that my model predicted it fairly well. The slight discrepancy, as you can see in this, which I showed you on my introduction slide, is probably the result of not including the drag force in my model, because although we don't include it, the drag force is still there in the motion, and it'll contribute not as much, but it'll still contribute in such a way where over time you'll start to notice the difference between my model's motion and the actual observed motion. Now let's address the what does it mean questions. Is the energy principle satisfied? In this case, a simple answer, yes, because the total energy, which is the yellow, which is the sum of the kinetic energy as well as both potential energies of gravity and the spring, equals 0. Now, it equals 0 because we included Earth, the spring, and the mass all in our system, and no energy was lost to the surroundings. So delta E equals 0, so the sum of the kinetic and potential energies has to equal 0. Now let's look at the second what does it mean question, where we compare the x period and the y period for the motion. For me, the average x period was 1.638 seconds, and the average y period was 1.519 seconds. Now they're close, but they're not equal. That's fine, however, because they're not supposed to be equal. Because in the x period, it's moving like a pendulum. It's moving in pendulum motion, so it's swinging back and forth. And in the y, it's a spring motion, so it's bobbing up and down along the spring. Now here's the equation for pendulum motion period, and here's the equation for spring motion period. As you can see, they're not related. The pendulum motion is related to the length of the string that's holding it and the gravitational constant, whereas the spring motion is related to the mass of the object at the bottom of the spring and the spring constant. So they're not related, therefore they shouldn't be the same. So our results turn out right. Thank you, and that's my lab.